Do you guys any questions, anything that's going on there? All right, so
explain a little bit about salting out.
oh, what salting out is? Yeah, this thing's right here, right? So you have this device screening length. So it's the idea that you have the train station, there's too many people in it, and the mother can't find the kid. So the concentration is too high. So you can't, so that means you can't, so that it's as if the kid didn't exist. Right. So if you put in, so the other people are the salt ions, like the counter ions, like sodium. If you put sodium chloride in, and if you have a polyanion, so it's screening out the interaction. So basically, it makes it so that there's no more polyelectrolyte. It's just a normal polymer. If you're spacing of the charges, which is A or B along the chain, is larger than that screening length. So you can put in enough salt that it's not a polyelectrolyte anymore. It's just a polymer chain. So it goes from a rigid rod and collapses down to just a coil.
Because they cannot find other.
It doesn't exist. So it effectively doesn't exist. So this is so that idea of screening, so that was 1926 in 85, van der Waal had a van der Waal model for interactions existed, right? So he came up with that, which is like, it's talking about excluded volume, and you end up with pretty sure it's 1885, but right, he had the idea that you have this kind of excluded volume B, right? And then you have a thermal interaction, like a binary interaction. So you have like A over KT. And that whole thing gives you this second Birol coefficient. So you have this idea that this would be like your enthalpic interactions, right? So this is what we have. So we have like this potential. We have this potential that's a Coulombic potential, like E squared over the dielectric constant. Right? Some kind of potential from the charges like repelling or attracting each other. And then you have this other something else. It's like this is enthalpic and this is entropic. Because in the end it's going to be B2 times KT. So anyway, this idea of like having that things can cancel out. So you have this enthalpic interaction. In van der Waals, it doesn't have to be Coulombic. It can be any kind of interaction. Like just so, and this is like a hardcore interactions when the gas atoms can't hit each other. Right. So the idea that something could cancel out that. So you have the ideal gas. PV is oops. So PV, well, PV over RT is going to be 1 plus 2 concentration squared. Right. So if this thing cancels out, you get the ideal gas law. PV is RT. Molar volume. So the moles are in there. So this means like this is like 1885, like the idea that you can make something disappear, like you have interactions. There's some condition where it would disappear. Like you say winds B2 equals 0, or if you say that the temperature is B over A or BK over A, that's like a critical temperature where you go to ideal gas condition. You have an ideal gas. So some condition, some temperature where you could get ideal gas, and then Debye says we could have a concentration where you get ideal, where it becomes an ideal polymer, say, or just the charges disappear. It's just a colloidal dispersion, right? Without this kind of without excluded volume interaction. So this idea of like screening was there. It was never put into the terminology that Debye put it into. like if you, so he had read van der Waals, that's like the thing that based all the thermodynamics on of interactions. And then he said like, well, there's a way to screen out these charged things too. It isn't exactly temperature. It's more like just this concentration takes a place of temperature and can screen these things. And then he developed this picture of like the 3D picture of things floating around and how you could lose the interaction with things. So that becomes like a fundamental idea of like that you can make, so there's a magic something like concentration or temperature or something else, electric field, where you can make interactions disappear. And then the system can, even though it's a non-ideal system, it can behave as if it's ideal. Right, so that concept you can adopt to other systems. Now, when you find it, you say, "Oh yeah, that's the same thing as what van der Waals did in 1885, and then 1923 for Dubai, and then 1958 or 60 for Florey." So we'll talk about how you can make the excluded volume interaction and polymers disappear too. Same way, and there's other systems where you can make things just like interactions disappear, so it can become ideal. But that's usually called a critical temperature. So then you have this whole idea, like the Landau idea of like a critical phenomena comes into it. So it all goes back to van der Waals. That's the idea. So some Dutch guy sitting in some little European town comes up kind of just like goofy model, to talk about gases. And it turns out that's the basis of all the models you have, not just for gas interaction, but also even up to Dubai for the screening, and then the other stuff grows out of that, So should all kind of fit together almost like a puzzle, in a sense. But anyway, Dubai screening length is the thing that can erase the polyelectrolyte. It can make it go through a transition. Like the homework this week, this Lee paper, he's got a polyelectrolyte. He looks at that does that. There's a Windows thing that it decides that you want to do this automatic scrolling, and then all right. So he has polyelectrolyte. This is a persistence length. Then you can make it by adding salt, and you can make it disappear. Like it goes from a charged polymer to uncharged. So it goes from a kind of a rod structure to a coil. So this becomes smaller. The persistence drops and the things become smaller. Right. So that's the Debye effect. Like you're putting the concentration and you're screening out the charges. It's like you're putting more people into the train station and the mother can't find the kid anymore. And the mother and kid distance is the charge spacing along the chain. So that's kind of, he's showing that happens. So anyway, so actually it's the whole polyelectrolyte thing is a little bit involved, and it's debatable whether or not you need to know about it. And it can get to be really involved. Like, so I've posted up this 2006. All right, so the other thing is that like this is a review from 2006. This thing has like 2,000 citations, which is a normal paper is going to get like 3, maybe 0. It's like 2,000 is a lot. If you get over 1,000, that's like a major paper. So anyway, this thing has 2,000. So all these polyelectrolyte things are getting serious hits, like seriously piling up hits. This box, so this paper is about alginate, which is seaweed, and then a calcium ion, and it'll make like a structure, a specific interaction where it makes like an egg. When you buy eggs and they're in the little thing. So the calcium will hold the polysaccharide rings in a cage, and then the calcium will sit in the middle like an egg. So they call it an egg cage structure. That's got 4,000 citations or something. Like that's a lot of citations. Basically, when they invented machine learning or something, that's got like 1,500. You know what I mean? So this is like all these polyelectrolyte things. So it may have no interest to you, but turns out in science, like this polyelectrolyte thing is like getting major hits. Like seems to be important, but if you're just dealing with extruding plastics, you aren't interested in it, you know. But if you're making a sulfonated polystyrene membrane for a battery separator or something, or then basically this has something to do with that, you know. So there are areas where it's important, and also if you're making soap or whatever, things that have charges on it, it's important, you know. So again, like, it's a little bit debatable how deep you want to get into this. Like, so that paper, this got serious hits on it. This is another, so you can, so this is pretty long. I mean, it goes through stuff we haven't covered in here, you know, like it's like a little book. Right. So we'll talk a little bit about the chain scaling and the blob theory and things. So it talks about electrostatic blobs and how it impacts this stuff. So but I'm not sure if we'll go through that exactly, you know, but anyway, you might want to take a glance at this and see just how deep it gets. I wrote down the page number on this where they talk about this OSF theory, which is, I mean, it's the only place where I found it, like a simple derivation of it. There's probably other places. There's another review on polyelectrolytes, this Chinese thing that I thought was really simple, but you'll find it challenging. And then this is this year. So this year, this review came out in Soft Matter. So it's like a couple months ago. It's just about polyelectrolytes. It starts out, it's the same stuff, like strongly charged, weakly charged, where they're important, and then goes through all this stuff about it. But when he gets to this OSF theory, which I had hoped he would derive it, he just says, like, this is it. Here's the final result of it. And when you read if you take a look at these two guys are like pretty famous polymer science people. Rubenstein wrote the book, wrote this book, Rubenstein-Colby book, which is kind of like the Bible for polymer physics classes now, I guess. But anyway, so he wrote this paper on, and Dobrin is kind of like also in that club, basically. There's some simpler, like a thesis from a university in England, and then some of the stuff here about the paper. But basically, those things are like kind of on the subject. You could glance at them. When you're doing the paper, you might want to look at it a little bit. They will definitely explain everything if you read them, but I think it's like pretty involved. So we just want to, I guess I'm just touching on the surface of something that's pretty broad and also has a lot of citations. So it looks like it's important in some aspect, you know. Anyway, so I've never published a paper on polyelectrolytes, so I'm not an expert at it. We've done stuff with worm-like micelles, which are charged. We didn't use this theory for it. They're charged chain structures, but anyway, so I'm definitely not the top person to talk about this stuff. But anyway, so we've got the Debye screening length as a parameter. 1923 came out. That's basically dealing with things like particle dispersions, and that ionically, if you have silica and water, it's got hydroxyls on the surface. The reason it disperses is because of the charge, and you can salt it out and precipitate it. The same with soap. Soap, like a molecule that's got a charged end group, you can salt out, and that charge of the end group goes away, and you just have wax. That's why soap kind of looks like wax, right? So it's because it is wax with a charge on it, and if you put enough salt, it just becomes wax, right? And if you put it into water, you dilute the salt, the Debye length gets longer, and then all of a sudden it becomes soap again, right? So it's wax soap transition is the salt concentration. So, and that's all the Debye screening length. In this paper, they're measuring this zeta potential, which is the potential that you can measure for a charged particle. So basically, if it's a spherical particle, so it's got a surface charge, hydroxyl groups, then the counter ion makes a monolayer around it. And then you have like a decay in that, an exponential decay that follows the Debye-Huckel equation, this exponential decay function. And the parameter of that is the Debye screening length that governs the width of that. And then they talk about the slip plane. So there's a stern layer, and then this zeta potential is measured at the slip plane, which is where the fluid, if driven by KT, just flows by the particle. So you have like free motion of ions out here, and you have kind of stuck ions here, and they become more and more stuck as they get closer to the surface. So the potential gets higher, and finally they're seriously stuck at the surface charge. Right, so we have a particle, say, what's the charge on the particle? The thing you can measure is a zeta potential. Like if you try to measure that, right? So to measure that, you're gonna like put the particle, first you're gonna put the particle in dynamic light scattering and watch it move around, get the diffusion coefficient, and use the Stokes-Einstein equation to get the hydrodynamic radius. So you can get the motion of it, and you can figure out from the diffusion Stokes-Einstein what the size in terms of equivalent spherical particle moving through the fluid. And it could be a chain molecule, it could be actual sphere. Then you're going to turn that off and put an electric field on the thing and watch the particle move. And to watch the motion, use a plasma. What do? You shoot you take a laser beam, split it into two, and shoot it at the particle. And you get a fringe pattern from that. And then from the shift in the wavelength of the fringe pattern, you can get the Doppler effect of the particle moving through the fluid under the electric field. From that, you get the velocity. And from the velocity, you can use Stokes' law, which gives you basically the size of the particle from the drag coefficient. See, from the velocity and the size that you got previously, you can back out the charge on it because you need to know the force that's pulling the particle. So you have like this. Sorry, in my mind I can see it, but I can see it isn't coming off my words. But yeah, so you know the hydrodynamic size because you watched it doing a little dance with KT, and then you put the field on it, and then the particle flies across at some velocity. You know that the force equals the velocity times the friction factor. The friction factor by Stokes' law is 6 pi viscosity times the RH that you already measured. And you can measure the velocity from the Doppler shift of the light coming in. So the Doppler velocimeter. So you can get the velocity from the wavelength shift. The light would be here, and it shifts a little bit to there in the presence of moving particles. With that shift, you can get the velocity. And then the velocity and the friction coefficient, you get the force, and the force is going to be like the charge on the particle times the field that you put on, this plus minus thing. So you can get the charge, like what is the charge on the particle? And what is that charge? That's the zeta potential. A little complicated. You can get this on Wikipedia. So basically, it's possible to measure the charge on the particle. In other words, what charge could you measure on a particle? That's the only one you can measure. You can't measure the surface charge because it's covered with counter ions, right? So you can't measure this diffuse thing very easily. At least I can't think of a way. So that you only have the one number you can get. So like in this paper this week, he gets the zeta, wherever that is. So actually, this is like a crappy little paper, and I thought it's too simple for you. But then I looked at it, and it's got all the elements of this whole thing in it. Right. And I also thought this is a screwy journal, like food hydrocolloids. All right. So I looked it up. It's got a citation index of 11. Okay. So like Macromolecules, which is the base journal for polymers, is 8. And Polymer, which is a decent journal, is like 5. So this is like a way better journal than any of the journals we're looking at, except for like Nature. Right. Nature is going to be like 40 or 50. So on the scale, this is 1/5 of Nature. So 5 papers in here would be like a Nature paper, which you think is kind of goofy, but in China, where these people are from, that's exactly how they're paid. They get money. If they publish a Nature paper, they get 5 times the pay. So it pays directly to the scientists. That's how they pay them. So basically, you're not going to see Chinese people publish it in like Polymer because it's kind of worthless. In other words, they get no credit for it. It's just like they do it just because they want to get it published. So they all are trying to get into like something above 10, and this one's 11. It's the bingo. So that's like you could put your paper in there. So why food hydrocolloids is 11, I don't have any idea, and shows you that I don't know much about like what's valuable and what isn't, I guess. I think food science, in the field of food science, which is a field, kind of a small field, probably Food Hydrocolloids is one of the premier journals because it's sciencey. And all the rest of them are probably about how to make cake pudding or something, whatever. So who knows? Anyway, turns out like this is a pretty good journal and it's a pretty good paper too. So it's kind of surprising a little bit to me. But so what was I going to say? I forget what it connected to. Connected to something here. Oh, they measure the zeta potential. That's all. It's not in this, it's in their supplemental. So there's that, and then they have a supplemental like everyone does, and got some weird things in it that it casts about in the paper, but they measure the zeta potential right here, zeta potential, and they measure it the way I mentioned. They say what machines, you can kind of look that up if you want, but that's the zeta potential as they add salt, so it changes. Right, so it goes towards zero. It's negative, so it's got a negative surface charge, and then it drops as you add salt. That's your piling up of ions onto the surface of it. So two things happen. You have the screening effect, then you have this thing, you're dumping ions onto the surface, then it reaches a plateau value. Like the charge goes to a plateau value. That's called charge condensation. So you have a rapid condensation of the counter ions onto the surface of the thing, and then it reaches a plateau value. And that plateau value depends on the temperature. So it's a balance between this Coulombic interaction and KT that reaches some kind of climatic point where it just has a fixed value after that. Right? That's a terminal charge for the polyelectrolyte, or for any kind of colloid has that same behavior. Right? So that's one of the features of these systems, you get charge condensation, which isn't shown in the kind of shown in this picture. I mean, you're getting crowding here. So that can be a lot of ions, like a lot more than what you think. So you have to keep in mind that, so you have a system of a thing being dispersed, right? And you have an enthalpic driving force for it, you think, because you have ions, kind of repulsive ion interactions that are making it suspend in the solution. Those two of these aren't going to get together because they're charged. But then you have this entropy thing, which is kind of a weird beast, right? So entropy doesn't depend on how big things are. It depends how many things are, right? So there's many ions here. So if you think about it, and these are free ions, so they have like 100% entropy. And once they get stuck here, they have zero entropy. And there's a lot of them, right? So basically, the system stability is going to partly depend, or could largely depend on just the loss and mobility of the counter ions, have nothing to do with the chain. Like, why does it precipitate out? But if you lose all that entropy, that's like a bad thing, right? So that means you could phase separate just because of the counter ion condensation. There's a lot of nuances like that in these kind of polyelectrolytes and soap and everything, right? So you can get a lot of different things. You have to think about them differently than you would just a chain wiggling around, right? So anyway, I mean, also water. So water is also in most of these systems, and water tends to order at a charged surface too. It can almost form a crystal form there. That's called like a hydrophobic effect can happen. So and the water molecules also have entropy. So you have big changes due to the ions organizing and due to the water organizing that you would normally just totally ignore. So say you do a computer simulation, and usually they have what they call an implicit solvent, which means you just have a background. The solvent's just a background. You don't see anything. You just say, oh, it's there, and maybe it's got an interaction with my stuff, but I don't really care about the solvent. I care about my stuff. Well, if you do that in a biosystem, it'll completely fail because all the actions going on is the water organizing around the stuff, and you've ignored it. You've made it into just a background thing. So you don't have the water. I mean, you have some kind of interaction, but basically you don't see the entropy change. The same with the ions. So you're going to do a computer simulation of these with lamps. You got to include the ions and you got to include the water, which means it's going to be like thousands of times more time consuming than the simulation that it would have been if it was just the thing, right? So anyway, so that said, so we got this Debye screening link, which is kind of the first step, the 1923 step of like getting the size scale where the that isn't a polyelectrolyte anymore if your charges are separated by that distance. And you see that in the some of the results from that paper. So you can have different kinds of polyelectrolytes, strong and weak, and they're kind of defined in terms of these, like the Debye length, the charge spacing, the Debye length, and these like how KT balances out against the charge, which is kind of the Debye length of the thing, right? So basically, mostly we're talking about strongly charged polyelectrolytes in this kind of thing, right? So anyway, so I mean, like if you read any of those reviews, the first thing they say is strongly charged, weakly charged. Like they distinguish between those, right? So then this other length that I mentioned in the last class is this Beaucage length, which is where the charges are kind of, so this is a point where the mother can hear the baby crying, but it can't tell what direction it's crying from. So that's a mean field. Like it's going to say, where's my baby? It's crying, but it will be turning around in circles, not seeing where it is, right? Versus going right to it. So if you're above the Beaucage length, you're in what's called a mean field. You can sense it's there, but you don't have a direction. And if you're below the Beaucage length, then you have a direction to it, and you get specific interactions happening, like the stuff will precipitate out. That's kind of the idea of this. So the Beaucage length doesn't have a counter ion concentration in it. It's just a number that goes with the charge, dielectric constant of the media, and then like KT. So it's just the ratio of the charge to the KT. Right. So if Beaucage, so per water, it's 7 angstrom. So 7 angstrom is a good number to think of that. The Debye length's longer than that. It's going to be a longer number. So you're going from specific interaction and then go into longer distances, mean field interaction. Then you go to Debye, no interaction. Like it's nothing happens after that. You don't see the charge at all. It doesn't exist. It's like a critical length scale where things just disappear. All right, so this is a picture that I retained in the slides. This is what we had for correlation function. We have like just motion of two particles. If you take one particle and then say what's the kind of the probability of finding another particle is some distance away from it. So you have a hard core, and then you have like kind of because you excluded particles from where your hard core is, there has to be a pile up at the surface. You have a peak. That would be your first interaction distance. And there's like some weaker interactions as you go further out. So like first level, second level, third level, fourth level. So it's kind of like a probability of finding, it's a probability of finding the material normalized by the average density in the system. So it goes to 1 as you wiggle out far enough. So you can calculate that in a charge system. You can calculate that number for, so you have plus and minus kind of spots or spheres. You can say like the plus spheres and the minus spheres. Or you can say the plus and plus spheres or the minus and minus spheres. So you get this kind of correlation function that the plus and minus are attracted to each other. So that just goes up to a big number as they get closer, and then the up to the hard core, and then the repulsive. So you have a dip for the plus plus for the repulsion. Right. So there's different ways to kind of look at these systems like that. Actually, I don't really know why that's in here, but it's there. Anyway, so we got the Debye length. So for polyelectrolytes, when you put charges onto a polymer, then you have to consider some other things. So let's see, I can get rid of this. So we have a charge spacing along the chain. So there's a linear charge density on the chain, like A. So the charge divided by A. It's like a charge density on the chain. There's counter ion concentration with the Debye, affects the Debye length. Then there's this issue of counter ion condensation, right? So I'll kind of go through that. I probably should do that first. And then so it isn't just counter ions that are acting, but also the chain itself has charges on it. So there's an issue of the polymers contributing to the Debye screening. So in other words, you're putting charge, when you increase the polymer concentration, each of the negative units, hydroxyl units, has a positive counterion, so you're adding counterions as you increase the polymer concentration. So your Debye, as you add more and more polymer, even without salt, your Debye screen length decreases automatically, which changes the properties of the material, which makes it kind of complicated. So you have the salt that you added in or had in the system, and as you add more and more polymer, the salt, the kind of effective counterion concentration goes up. So you're just adding more polymer shifts the Debye length, makes the behavior different. So it's complicated. It's not such a simple thing. These are like the simplest things of it. It's more complicated. If you get to two, yeah. Yeah, it's directly related to it, right? It's KT. It's square root of KT. So Debye screen length square root of KT, because the balance between the electric keeping track of the counterion concentration and KT. So it's kind of balancing those two things. So 3 years later, Bajiram said just KT and the, let's see, the Bajiram length, oops, here. Bajiram length is just E squared in KT, and then this Debye length is E, and then the counterion concentration is E squared times the counterion concentration. So the difference between the two is this is like counterion, and it's where the charge totally disappears, and this is just the charge, and it's where you go from specific to mean field behavior. So they both have KT. They're both like balancing KT and some energy. The energy is just the charge energy, or it's a charge times the number of concentration of counterions. Yeah.
I like the bio, like I know it's hard, but what does that mean?
Well, it's this function. So this Debye Huckel, in other words, this is an exponential decay. So this is going to be R over RD. Like the breadth of this decay depends on RD. If RD is larger, this is a broader, it's a slower decay. And if RD is smaller, it's a faster decay. So you could say like when the total maximum potential reaches 1 over E, like when it's minus R over RD and RD equals R, and that's 1 over E, which is like 30.37%. So when this potential reaches 37%, that's RD. So it's kind of a simple, yeah.
The charge from the surface can be measured, cannot be measured. But
Right.
it applies to all scenarios. Like, is there no way one can measure the changes in the surface?
I think no. I think that only that you made, well, you can do, if you have silica, right, and then you can do a measurement of the silanol groups on the surface with IR. So you can stick your silica into IR and you can count how many silanol groups are on the surface. And then you can multiply that by 1 E each silanol group, and that's a charge, and divide by the area of the particle, then that would give you the charge, that would kind of give you the particle charge, or multiply by the area.
So, from what you've been explaining, the balance is caused by the counter ions.
Yes.
So the counter ions dominate like the silica get attracted to other counter ions in the solution.
Yeah, they just wash out. So it's like you get the train station is so full of people that you couldn't tell anything's going on.
Some other ions absorb on the surface. Like for instance, this.
Right. Yeah. So the charge of the particles changing is this. So you have this zeta potential, but it drops as you increase the salt concentration because of this condensation of the counterions. They come in and make a solid counterion thing on the surface, right? So you can, so let me just do that. So that's called counterion condensation. It's one of the features of these systems. So that's like not there, it's here somewhere. So it's just a balance between, so this is how it works. You have, all right, so the counterions, you can think of them as a gas atom, like floating around. So you have like an ideal gas floating around. So you can say, well, there's a pressure. So they're kind of say the counterions are confined to a tube around the polymer. Right, this for polymer. So condensation can happen for spheres, but it could happen for polyelectrolytes too. So you have a region where the counterion is confined, right? They could move out further, or they could come in closer. But say you have one size that they have, so that's this size volume, right? So you say the internal energy is going to be PdV in the absence of Q. That's the thermo equation. Then you say the internal energy. So if you let's see, you can substitute ideal gas P equals RT over V. So you have RT over V, dV over V. If you integrate that, you get ln of V. So ln of V2 over V1. In other words, it goes from being confined to V1 to confined to V2. It changed, right? And that's the energy of taking the counterions and letting them move out. That's just an entropic energy effect, right? And you can also do an enthalpic and talk about the potential. So there's two E's, so it's E squared and then divided by R gives you the divided by R, dr by R, that gives you the enthalpic potential. So you have entropic, enthalpic, right? And then if you integrate that, you end up with ln of R2 over R1. But if it's a rod, the volume is proportional to R, so it ends up being V2 over V1. So then you can balance out these two guys, equate those two, like this is an entropic driving force, that's enthalpic collapsing or condensation. The V's drop out and you just have this relationship between the charge and the temperature, kind of, which gives you this number U. So you use like the charge energy versus the thermal energy, right, between the two. So if U is less than 1, the charge energy is smaller than the thermal, so it's going to expand. So the counterions move out. If U is greater than 1, the charge energy is larger than the thermal, so you get condensation of the charge. Right? So you have this kind of parameter U that shows up for this stuff. That's 1 is the cutoff point where you have equilibrium. So if you think you're having the charges come in, and then your U is changing. So basically, at some point, the thing equals 1. Like if you set this thing equal to 1, then you have like an effective charge on the chain. It's a final charge when it would be condensed on it. And from that, you can plug it back in and get the size. So you get the kind of diameter of what the condensed charge is. So if you're at low concentration, you're going to have this entropy is favored, the counterions move out. Then as you increase the concentration of the counterions, U approaches 1. And once it reaches 1, it gets stuck. And at that point, you have a fixed charge on the chain. That's the idea of this. So that's what's shown in that paper. I can get back. Yeah. So here's the zeta potential. So you go and you add counterions. It goes, so the charge on the chain drops as you add the counterions, and then it reaches a number. That's this fixed value that you get because you've added too many, and then it's just a constant zeta potential after that. That's measured by this moving the particles around thing. Right. So that's demonstration of this counterion condensation in action, I guess. Yeah.
If the counterion and solvent molecule affects the behavior of polyelectrolyte.
Yeah, I mean, it's changing the screening length. So if you put enough counterions in, it turns from a polyelectrolyte to not a polyelectrolyte. Like it goes away. And also the other effect is that as you add the counterions, you get this condensation. So the chain charge drops as you add more and more counterions because of the condensation of the counterions that oppose the charge of the chain. But that only goes to a fixed point to this, once it'll saturate at this condensation level, or where this U effective equals 1. You don't get any change after that. So it's complicated what happens with counterions. And this is like the simpler end of it. These are only the basic points. So if you read those chapters, there's a lot of other stuff so it gets so complicated, it's like useless, right? So I think to me, it reaches a point where it's kind of pointless to keep talking about all these crazy things that people have come up with about, and every year there's more stuff coming out. And every year there's like 1,000 citations for the paper. So it seems like it's a big area of interest. I don't know, but anyway, so yeah.
Just curious, it's like the ions make the electrolytes, like, they make them maintain, like, for instance, if you want to do like size measurements, like measure the, measure dynamic radius of the polymer. Looks like the counter ions makes it easier to measure.
In what sense? Because I mean, you get, all right, if you're doing X-ray scattering, the counter ions have a lot more contrast in organic polymer. So you basically just see, like if you do X-ray scattering on this stuff, you just see the counter ions because they're metal. So metal has a large electron density. This becomes complicated to try to analyze because you'll see these, what you'll see is a lot of peaks. So if you stick it in a neutron beam that only sees the hydrocarbons, you see this featureless decay. If you stick it in an X-ray beam, all you see is the counter ions. So all you see are these shells of ions, and they're regularly arranged, so you get peaks, like diffraction peaks. So analyzing the two, the one is like kind of crazy because it's too many peaks, and the other one's pretty vague because it's featureless. Yeah. So to get the structure is kind of complicated. So there's different features to these systems, like the analytic parts of it are kind of difficult in some ways. I mean, hydrodynamic radius you can measure pretty easily. Light doesn't see the difference between metal and organic. So anyway, so that's the kind. Any other? I don't know if yeah. No, the charge, the zeta potential reaches a plateau. So that's what you see here. Boom, it reaches a plateau. Yeah. Yeah, when U equals 1, that's right here. Like it goes up, 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 and then boom, it equals 1. So it's not a zero charge on the chain. Let me blow this up a little bit. So zero's up here. So the chain never reaches zero charge. If you're adding more and more counter ions, the charge, because it counteracts the surface charge on the chain, it drops, or the zeta potential, and then finally it reaches a fixed value, but it doesn't reach zero. It doesn't flip sign. It keeps the same negative potential. Like it's an anionic, it's a polyanion. So it's negative, 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 never goes plus. So the counter ions can't wash out the negative. If it's at zero, it'll precipitate out, I guess. It doesn't have any charge holding it into solution. So it never comes out of solution, it just reaches this number. So there's a plus counter ion and a negative counter ion. So they're in like, so you have the negative chain, then a plus, then a minus, then a plus, minus, plus, minus, plus, minus. And finally it reaches this point where it's fixed value. That's the model for this counter ion condensation thing. It's like I said, the whole thing is pretty complicated. Like it gets to be more, and this is a simple part of it, So is that okay or? All right. All right. So we got that. That's this counter ion condensation business, which is mentioned in the paper. I mean, so it's good. Then this idea, so this is a OSF theory. So we have the idea that we have like the persistence length of one of these chains has like a base persistence length, and there's an electrostatic that just adds to it. So it's kind of a simple way to look at it. The evidence for how that works, I mean, it's hard to tell that this, anyway, that's what they said, and this was 1968, the OSF theory, right? So, and there's a couple other theories that came along, but this is the main one that people talk about, right? So this is the one that and then he mentions in the paper, he's got two theories, this and the BJ theory or something. So OSF, the reason it's called OSF is because this is the guy's names who did it. Odijik, Sholnik, Fixman. Fixman's kind of easy for me, but the others are like Norse or something. I'm not sure what. So they're going to be like, basically just call it OSF, right? It's one of those there's definitely a reason why they came up with that name. So anyway, the idea is like, what is this electrostatic persistence? Can you calculate it? And particularly in terms of the counterion condensation. So they did that. So they did it kind of in terms of this thing called a Manning length. So if you take the charge separation distance, which they call B, and in other places they call A, and sometimes B is the persistence length. So this makes it really confusing to look at this. Like if you find a paper and then you just find the equation, you have to really search for what is B. So B is the spacing of the charges along the chain, which is called A in other places, right? Because B is usually the persistence. But anyway, the Bejirum, which is this length where the mean field shows up, divided by B is called this Manning length, which kind of says if it's bigger than 1, you're in mean field. If it's less than 1, you have specific interactions. Or let's see, the other way around. If it's greater than 1, it's specific interactions, less than 1, it's mean field. So you can have different charge spacing on a chain. You can define what kind of interactions you're going to have with it. Right. And again, LB 7.1 angstrom, and yeah.
Who's the
That's the dielectric constant of, or permeativity of free space. And the eta is like a shift factor for that for real things. And the units are going to be like Coulomb per, I have the units of that here somewhere. Energy is KT, CV, units of are Coulomb per volt per meter, Coulomb per voltmeter, right? Or Faraday per meter is the dielectric. So if you plug that in here times length gives you Coulomb per volt. So Coulomb volt is energy. Anyway, somehow you need to figure that out to figure out the units here, right? So anyway, it's basically the capacity of the material to hold a charge, the dielectric. So anyway, so that's what that is. Let's see here, right? That's good. So yeah, so you have this equation just relating the Bejirum length to the charge spacing, and saying like this gives you this number 1 means something. Then if you look at this, this is what comes out of the OSF equation, is this function for this electrolyte contribution to the persistence, which has this Manning parameter in it, like LB by B is a Manning parameter. Then it also has K, 1 over K is the Debye length. So it's got the Debye length in it too, also normalized by B. So you have kind of, if the charge spacing is above the Debye length, it's not a polyelectrolyte. And if it's below, then it is. So you have these two times each other, then you just have the Debye length as a persistence, electrostatic persistence length. Right. So it's kind of like the Debye length kind of modified by something. Right. So the result of the Bejirum is kind of the Manning times a reduced Debye times the Debye. So it's kind of, I think about it as just the Debye length, Anyway, so we have that added feature. This is the only place I could find easily. So this is linked up there, this Dobrin Rubinstein 2005, where they actually kind of derive this equation for the electrostatic persistence contribution. And the way it's derived is that you have a rigid chain, you bend it, the chain has regular charges on it. The distance between the charges, because you bent it, changes the free energy of the chain. And you can change, so if you have 2 different bendings, so straight and then bent, then you can have a change in the free energy. And if you say like the amount of bending, so if we had, let me do that too. All right, so we had for the persistence, this business, exponential minus S over the persistence length, which is the same. So this exponential decay is like all over the place. That was our 2 tangent things, right? Tangent dot tangent at S and 0. The average value of that's this thing. So, or divided by some, maybe that's just it, just equal to that, right? So anyway, if you say, so the dot product is like, say they're unit vectors, so it's 1 times cosine of the angle, right? So if you say, so if you're say like S equals LP, then I have I have 1/E equals cosine of the angle, which gives me 68 degrees. So that means when my S is SP, which is at my persistence length, so if I have the tangent here and the tangent there, if the angle between those is greater than 68 degrees, then I say that's LP for the chain. Right? So I mean, you can just say like I can figure out I'm going along and then like, oh, I turned a corner. Where's the persistence length on that? Well, I just draw some tangents, and when that angle's bigger than 68, I can say, well, that's my LP for the chain. Right, so you can kind of graphically do that. And that's what they do in this paper. They in fact don't do light scattering, neutron scattering, X-ray scattering. They take pictures of the chains because they're pretty big chains. These polysaccharides are almost a micron in size. Right. So basically, I'm sorry that I didn't realize that thing was zoomed like that. Anyway, so right, so let's see. So anyway, this is doing kind of the same thing. They're getting the angle, so they know it's going to be 68 degrees for the persistence. And then they have this function of the energy as a function of the angle, and they can kind of figure out what the persistence is going to be for that by adding. So they're kind of doing that exact thing. Just, I mean, they don't say exactly that, but I think that's kind of what they're doing. So anyway, no one explains this equation anywhere very well. And I think I haven't looked at the original paper from 68, but basically, I think probably the original one didn't do much of a job on it either. And if you look at it too carefully, you probably wouldn't believe it type thing, you know. So, but nonetheless, this is the equation people use. So you're going to get this persistence goes with the square of the Debye length, and Debye is 1 over the square root of the concentration of the counterion, which means you're going to end up with a linear dependence of this on the counterion concentration if you plug in everything, which if you look in the paper, that's what they get. They get exactly that. Not just that paper, but everyone else gets exactly that too. So you have a theory they propose that looks a little goofy, like you can't exactly figure out what's going on. Then you have a bunch of experimental evidence. It's exactly the answer, you know. It's like everyone puts a lot of merit into that thing, so that paper gets a lot of citation. And then the more they discover it, the more they believe it. So it kind of piles on itself. And it's probably true, you know. Who knows if their reasoning is really this, you know. This is a little bit of a strange reasoning for it. Anyway, so that's that business. We got counterion condensation. We got the this OSF model for the persistence. That's in the papers. That's good. And then what else is here? This is just showing. So his graph shows. This is a schematic of what the guy shows in the data. This is a zeta potential. It goes up and plateaus out at this magic number that can be calculated. You know, it's a dielectric in the charge in KT. So he's getting the same number. I think that this repeats itself here somewhat. So what else we got? Yeah, so next time, so that's kind of it for the polyelectrolyte. Any questions and stuff? So we'll go through a paper on this. That is exactly those points. So it's kind of useful. And again, it's kind of a simple paper in another sense. This stuff isn't that simple. So it's in terms of this stuff, because you could, like the guy, we reviewed the paper of Colby, like he's written a lot on this. And if you pick up one of his papers, it's like kind of more intense. It's going to have a lot of different concepts in it, and you can't tell which ones he invented and is just pushing forward in that paper and what's actually believed. You know, whereas this paper is just what actually the facts are. You know, like whatever that cop show used to be, the facts, nothing but the facts. But anyway, so it's good. It's good to kind of look at this paper because it's like state of the art. Right? It was published this year and everything. So anyway, so yeah, so after this, I'm going to go through something about the tube diameter. Like we talked already about packing length. I'll talk a little bit about that, more about that. Like I'll go through the derivation of where that originated from. And then we're done with this section then finally. So basically early next, like Monday, I'll finish this thing and then we can go on to like chain scaling, just like part 2 of this. So this is kind of finishing. Part 1 originally was very short and now it's grown into this long thing. But we've covered a lot of other things in context of it, so that's good, I think. I think it's not really a waste of time, but any questions or anything on this stuff? I can kind of quit there. All right. All right, thanks, yeah.